Hello everyone. This video is going to serve as a tutorial for an introduction to negative binomial models using R software. I'm Tim Barrett. This video was originally filmed to be used for CE 552 Traffic Safety Operations and Maintenance at Iowa State University for the spring 2017 semester. However, the subjects that we're going to cover would be much more broadly applicable than just that use. To work along through this tutorial, you will need to have R and RStudio installed on your computer. We covered how to install R in a previous tutorial. This demonstration will be done on a computer with a Windows 10 operating system, but again, the procedure would be applicable for computers with other operating systems. So some of the topics we're going to cover would be creating an R project directory, which I find very useful for managing my files, especially if I have a variety of different analyses going on at the same time. We're going to go over how to use the help function to gain insight as to the applications of various functions and packages. We're going to go over how to recode variables in R, which is demonstrated in some relatively simple syntax here on this page. We're also going to go over several functions, including the read.csv function. You can see I've identified the syntax that we're going to use for each of these functions. And generally, when I do any sort of read function or any sort of model, I'm going to save both of those as objects. And that's why you can see that my data here would become an object dependent on this read.csv function, which is going to read in a CSV file called my data in this hypothetical example. We're also going to go over how to use the library function to pull packages that are installed into your computer into the R environment and R project that you're working in. We've gone over in our tutorial on how to set up and install R in RStudio. We already went over how to download a package, but you'll see that again. We'll go over how to plot, how to do a simple plot. Again, this is the syntax that you're going to use is shown right here. We can say that my data would be the data set, and then it's separated from the variable we're interested in plotting by a $sign, and then we'd have our x variable, and we do the same thing for our y variable, and that's how we can make a very simple plot. There are other options that I'll let you explore on your own that would allow you to manipulate the area of the plot or the axis titles and so on and so forth. But we're not going to cover that in this tutorial. The major focus of this tutorial will be how to use the glm.nb function, which is generalized linear models negative binomial function. Once again, we can see that I've created the way that my syntax is set up. I will create an object called my model that is the result of running this function, where y would be my dependent variable, and it would be based on, in this case, two independent variables, x1 and x2, and I specify my data set here. There are other options you can play with, but those options will not be covered in this tutorial. Two common functions that are built into R that we'll be using here are the log function and the offset function. So it's fairly common that we'll want to do a log transformation, or in our case, a natural log transformation of some of our variables, particularly our exposure variables. And so we will show you how to do that. We'll also show you how to use the offset function so that you can identify a variable within your model that will have its coefficient constrained to be 1. This is commonly used when we do roadway segment models, and we want to constrain the length, or at times you may want to constrain the volume as well. We'll go over the summary function, which is going to spit out a nice output of the model we create. So that represents what we're going to cover in this tutorial, and I hope you find it useful. So the first thing that I want to do is I want to log into Blackboard for this particular example, or essentially I'm just looking to locate the data set that I intend on analyzing. And in this case, we're going to work with a data set that comes from the state of Iowa and looks at the frequency of crashes on curves on divided rural highways. And I can see that I have that data set here, which I've called curve frequency data. So in this data set, each row is going to represent a specific curve over a period of 5 years. So that essentially every entry is 5 years of crash data summed in one line. So I'm just going to download this to my desktop. Before I get too far involved in that, I want to create a new folder that I'm going to use to save my work. And again, I'm just saving on the desktop, but you can save to whatever location you like on your computer. And I am going to call this particular folder R curve demo, and I will save my data set in this folder. You can see that the file format that I'm using is CSV, or comma separated value file. This is the general format that I save data in when I intend to work in R. You can save using XLSX files. However, you need to install additional R packages to make that file format function properly. So for our case, CSV is going to work just fine. So now that I've downloaded my data into the appropriate folder, which we can see right here, I'm going to open RStudio. And I'm working with a dual monitor setup, but I only have the screen capture tuned to one particular monitor, so you might have to bear with me if I have to transfer various things from side to side. So the first thing I want to do anytime that I work in R is I like to create a new R project folder. And as you can see, when I just opened up RStudio, I was brought into the most recent project folder that I had open, and you can see I was working on a model here for TRB, but now I'm going to create a new project folder. Project folders are nice in R because, as I said, everything that I was working on that I saved in this project folder and had open the last time I had RStudio open opened up right away. So it's an easy way to pick up where you leave off in when you're doing work in R. I am going to select the existing directory option, and I am going to create my new R project in the folder I created and saved my data in. So I will go to the desktop and our curve demo and select folder and create the project. And now you'll see all of these tabs are going to go away. And I'm going to get a new sort of blank slate to work in. Okay, so now much like the first time that we installed our studio in R and we were playing around a little bit, you can see that I have three windows here. I have my console, and then my environment window and my files window. And so the first thing I want to do, once again, is create a new file. And if you recall, I prefer to work in R Markdown due to the fact that we can make publishable HTML or PDF documents. So I'm going to select R Markdown. And again, I will title this document R Curve Demo. And why don't I specify that as R Curve Frequency Demo? Because eventually we are probably going to want to run a severity model. So you can see that here I have a new R Markdown document, which is going to come into this upper left quadrant of my screen. So to make things nice, I'm going to just maximize our studio. And now I will get us going with R. I generally delete out some of these. These are just kind of some demonstration codes. And so I just tend to like to just get rid of them. However, in your first time playing around in RStudio and in an R Markdown document, you may choose to explore these options. And again, for my purposes, I can just clean up this little window. What we have from lines 8 to 10 here is what is referred to in R as a chunk. And so I can separate the code that I'm going to use to analyze my data set into these various chunks, and then eventually I'll have the option I can run specific chunks rather than manually identifying individual lines, or depending on what my needs were, running the entire code, which, as you can imagine, sometimes the code can get quite long, and it's not necessary to rerun every line of code every time. So the first thing we need to do is bring in the data set that we intend to analyze. And ordinarily, had we not gone through our process of setting up our project folder, we would have to do a little bit of code to properly set our working directory. But since we have this project folder, or this R project, located in my R Curve demo folder, RStudio will automatically know which directory I'm looking for when I want to pull data. So I am going to read in the data. The first thing I want to do is I want to create a data set that is going to be called, I'm going to call it Curve FREQ, Curve Frequency. And it's going to be based on using the read.csv function. And you can recall my specific data set was called Curve Frequency Data 12/28/2016. .csv, you have to include the file extension. Also, when you use this command, your file name has to be surrounded by quotation marks. So now I can run this line of code, and you'll see in the global environment here, I will get a new object called curve frequency, and it will be all the data contained in this document. And I can run this line of code in a variety of ways. usually for me, the quickest way is just by keystrokes, which is using Control Enter. And you can see it ran the line of code. Now, one option, depending on the version of RStudio you have that you might want to play around with, is this chunk output inline or chunk output in console. And this will come more into play later, but just to generally speed up the computation process, I do chunk output in console, and then everything I do is going to be documented down here. This option that's currently selected by default will display my modeling results up in the R Markdown document, and I found that it's just kind of slow and unnecessary, so I like to use this particular option. And you can see there's no output actually in my R Markdown document right now, but I generally just click Remove Output and keep all my results down in the bottom left and all my code in the top right. So you can see that this curve frequency data set is 471 observations. So we have 470 curves and 83 variables. Now, one thing I can do to make sure everything came in right, which I'm fairly certain it did, is I can actually open the CSV file. And we, of course, can then scroll to the bottom, and we see that the CSV file ends on line 472, which indicates that there are actually 471 observations. One thing that's nice about R is that you have a little bit of flexibility in how you recode variables. So certain times you would have a variable in your data set and you might decide, for instance, if we look at this limit miles per hour, which is simply the speed limit on these curves, I at some point might want to recode that into speed limits into a series of binary indicators. And in fact, I've actually done that already. But if I hadn't, I could do it either in Excel or in R. And we'll go over how to recode variables in R. But it is nice if you don't feel like actually writing the lines of code. You can just simply make your changes in here and then reload your data set and approach things that way. So we brought in our data set and created an object named curve frequency, which we can see here and here. The next thing I need to do is load the appropriate packages to perform our analysis. And as I mentioned, this is a curve frequency data set, so we're dealing with count data, and we are going to use what is generally the standard in traffic safety modeling, which will be a negative binomial model, and that comes from the R package mass. So to get mass on this computer, the first thing I want to do is come over here to packages, install, and look for the package mass. You can see it comes up, so I just select it, and I'm going to hit install, and we can see down in this area, R is installing the package. So now that I have mass installed, I want to make sure that in my code, and this will be more important if I close this and then come back to work later, but I want to make sure that my code will allow me to, will know to bring in that package if I leave and come back. So I simply do library mass. And now if I run this code again from top to bottom, I'll always call that mass function. I'm just going to run the line. And you can see it ran the code and it's done. And there we are. So we will do a little example. I'm going to call this top chunk of code I'm just going to label it read data and call packages. Okay. In our markdown document, these pound signs prior to this text are going to indicate the size of the font that I'm going to use in this when I output. I'll just show you a quick example. So as I mentioned before, we can create publishable documents, and we do that using the knit command. So I'm going to knit to HTML, and we'll save it right in that project, and I'm just going to call it knit demo. And UVR is working, knit, and then it creates a publishable document. And so I could control this font size by changing the number of pound signs I use prior to this text. So the next thing I want to do is just do a quick plot to demonstrate how to do a plot. If I were just working for the sake of getting documentation to show up in this console, it would not be a big deal for me to use this notation. This notation is specifically for that knit function that I used before, and it controls what would be put in that HTML document should I use the knit function again. So this is how you kind of denote separate chunks of code. I just want to do, well, I guess before I do plot, I'm going to show you another way to check in on your data to see how it came in, and it'll also allow you to see how your data was labeled. So certain symbols that are commonly used to denote various variables might not necessarily come into R properly. So I'm going to show you a command that will allow you to investigate that, and it is called the head command. So I will do head and then curve freak. So head of my curve data, and that is going to show us the names of each column, and it's also going to show us the first 5 entries or the first 5 rows. So just scrolling through, I'm not seeing anything that really jumps out as unexpected. I take that back. So non-freeways. In my data set here, the CSV file, we had a non-freeways. And so we can see that R, when it read in this data set, it replaced the hyphen with a period. And that'll be important when we go to write our little line of code that's going to actually run the negative binomial model, because the one thing about one of the important thing about how you set up your R models, and you'll see it in the future, is that R is you have to spell out the name of the variable that you want to include in a model. So it has to be properly spelled, and it has to be it's case sensitive. So when we're calling out variables, we have to match whatever we have here exactly. So here we're going to see how to just make a simple plot, and it's just simply the plot command. And I want to plot, let's do what is going to be a good one for our model. So we want to plot our exposure measure versus our dependent variable. So our exposure measure in this case we're going to plot it as ln AADT divided by 2. So the way our data set was initially structured is we had traffic volume given to us, two-way traffic volume, even though the roadway is divided. So we divided it by 2, and then we did a natural log transform. And we are going to investigate just total crashes here. So we can see we actually spelled out the words total crashes. And we see, in fact, that it could not recognize this bit of text ln AADT divided by 2. So the first thing I want to do is I want to check to make sure that I spelt everything properly. Another thing that's useful in R is knowing how to call the help menu. So if I have questions about a specific function, I use a question mark and I type in the name of that function. And I did it outside of my chunk because I intend on deleting this and I don't want it in the actual published document. And so you can see that down in the bottom right, now I have help regarding my plot function. And generally we can scroll down far enough and we'll see some sort of demo that will show us how to further specify. I'm just trying to make as simple of a plot as possible. So we can also generally see the structure that's used in calling these functions. And so I have just recognized my problem, and it's with the plot function. It doesn't realize, because I could potentially have multiple data sets or data frames loaded into my environment at the same time, it doesn't realize where these variables are supposed to come from. So I need to include that in the specification of my plot as well. So doing that is as simple as typing the name of the data set, and then we use the $ to separate data set from variable. And again, they're both from the same data set, so I use the same. Now when I run this line of code, it should hopefully work. Yeah. So here we can see we've just got a quick and easy plot. And I guess we see is about what we'd expect with our data. Kind of, it's hard to really tell with the overplotting, but yeah, it's about what we would expect. So again, on the x-axis, we have the natural log of AADT, which it says divided by 2, but what it really means is directionally. So AADT was given as two-way. For example, both the north and southbound directions of a divided highway. And my curve level data is direction specific. So I divided by 2. That way we're only looking at either the north or southbound volume. Now I would like to, I guess we'll run our first model. And it's just my habit to create the start and end point of my chunk. Feel feel free to work in whatever fashion you see fit. So I am going to call this first model NB1. And so that's just NB for negative binomial. And we are going to now demonstrate the code. So I've already called my mass function, so I don't need to worry about that. Now to run a negative binomial model, we need to know what specific function within this mass package we need to use. And I know it off the top of my head. It's called glm.nb, or generalized linear models dot negative binomial. But if I didn't know that off the top of my head, I could look for help in the mass package. Also, because R is an open source software, there's always multiple ways to tackle specific modeling needs, and there's a ton of resources available online to help you get going. So I use this double question mark mass to look for help for this package, and here I can see that it comes up over here. So I click, and so I can now identify what functions are available in mass. I'm not necessarily seeing the function I want to use, so I guess we will probably circle back to that. As I said, I know that I want to use the package called glm.nb, so let's just do a quick search of that, and let's see what happens. Okay, so we can see that glm.nb is in the mass package, and it's just fitting a negative binomial generalized linear model, which is exactly what we expect. And here we have some information about how to use it and some of the default settings that you could eventually tweak if you so desired. Also, we see some examples of some things that people have done. So when we program a model formula, we can see this is our dependent variable on the left-hand side, and then the independent variables on the right-hand side, and then our data, and that's just the simplest form. So let's get to it. Now we can recall that we're interested in total crashes, and because I'm going to specify what data set this comes from at the end of my formula, there is no need for me to precede any of my variables with the data set. You do not necessarily have to put spaces in between characters. I like to because I think it looks a little bit neater. So we discussed plotting against our exposure variable, which in this case is the ln of the AADT divided by 2. Now, I have specified that in my data set already, which we can see if we scroll to the right far enough here. However, if I wanted to, I could recode this variable in R. And since that's probably going to come up for someone eventually, I'm going to show an example of how to do that before I get into running the model. So once again, I'm just creating a chunk. And this is more just to help all of us keep track. So I'm going to run several little chunks, but there's really not a need to do one chunk for every line of code. But this is just, since we're early on, I want to make sure that things are easy for everyone to see. So we want to recode the AADT 5, which just said it's the 5-year average of AADT on these curves. So the first thing I need to do is call my data set, and then I need to name what I want the new variable to be called. And so I will call it demo AADT. Then I use this arrow sign to just say everything on the left-hand side is going to be based on what I put over here on the right-hand side. This is a common operator that's used instead of the equal sign in R. So the ln function is not built into R. I want to use the log function. And log by default in R is the natural log. So if I wanted the log base 10, or what, I would have to specify log 10. So I will use the log function. And now I'm going to call out my variable. It's curve freak $sign AADT 5, and you can see the little menus pop up to that I can just select as a drop down if I wanted to do that, if I didn't know the exact spelling of a particular variable. And as I mentioned, we wanted to make this divided by 2 so that we're only capturing AADT traveling in one direction. So I divide by 2, and if I hit Control Enter, we can see that I recoded the data. And a subtle change was that my data set now, instead of having 83 variables, actually has 84. So if I were to revisit that head command, we can see that appended to the end of my data set, I have that new demo AADT. So since I have my AADT calculated, I'll just enter that into my formula for my negative binomial model. And that is a simple formula, and so now I can actually run my first negative binomial model. And you can see that it doesn't look like anything really happened. However, if we look over into the environment window, we see that I do have an object called NB1. So in effect, what happened when I ran this line of code is I created a new object that contains the output of this model. So if I actually want to see what was done with the model, I have to use a function called summary. And now when I run this line of code, I can see the output from my model. So in the console, we see the lines of code that were run, and then we see what each line did. So obviously this NB1 function, it called the glm.nb formula and ran it with total crashes as the dependent variable and demo AADT as the independent variable. And then the data was curve frequency. And then this is the initial theta. Theta is the dispersion parameter of the negative binomial distribution, and in a somewhat opposite fashion of what some of the other statistical softwares do, it gives it in terms of dispersion parameter, whereas we're probably used to hearing it as over dispersion parameter. So we just need to remember that if we're going to use this for an empirical Bayes application, we need to take the inverse of this number. Here I can see the estimates of the intercept and the coefficient for demo AADT. In this model, they're both highly significant, so p-values much less than these default values. So it's a good start to the model, but one thing that we want to consider is that I have not, this is not a very highly specified model right now. We only have one variable, so we're going to want to expand on that a little. And the first thing we can do is, because we're dealing with curves, which is a length of roadway, we want to add something in to capture the fact that these curves do not have the same length. So I need to add in a length variable. So I'm going to go to my data set to recall exactly how I've coded length. You can see I have curve length in feet, and that's the one we're going to want to use for this. We're going to take the log transform of this, and I'm going to show you, instead of using this, which is already neatly coded for us, I'm going to show us how to just do a log transform directly in our negative binomial model code. If I want to add additional parameters to my model, all I have to do is add a plus and just type them out. So let's type out curve length feet and see what happens. So I just rerun the 2 lines of code that I've written, and we can see some information about our model fit and about our theta parameter. It's fairly common when we're modeling roadway segment data to use that length as an offset. So I'm going to want to transform, or I'm going to want to call that an offset variable, which is going to mean that instead of this coefficient being very small, I'm going to constrain it to be 1. I'm also going to do a log transform of curve feet. So to accomplish the goals I just laid out, I use the offset command. And then again, I have to call the log function because I want to take the log transform of this. Length value, 2 parentheses to close it. And actually, we are going to do something a little different. Rather than changing this model, why don't I create a new model that I'll call NB2. And this way, we can track kind of the various changes we've made to our model. So it was as simple as copying and pasting. So now I can run this model. You can see I have a new object that came up in my environment, and then when I run the summary, we see that I no longer have the length variable listed in the coefficients. That's because since it's now an offset, we know that that coefficient is constrained to being 1. So with that, I'm going to knit one more time to save our progress. And you can see because I have these head functions in, I get a bunch of junk, and then it's going to show my plot. And then again, we see the head function. Then it's going to output the summaries of my model. Now, one thing I should show is that I don't need to run it and save it. I can just run this code. However, what we'll see is that the output is not necessarily as neat, and I don't get all the information that I want. So generally, it's better to run the full, save the negative binomial model as an object, and then do the summary. So far we've discussed how to run models with basically the bare minimum of parameters. But ultimately, when we're running these models, we are trying to identify the effect of various roadway characteristics, roadway geometry in particular. And these functions alone don't allow us to do that. So we are now going to estimate a model that is going to allow us to look at the radius of the curves that we're analyzing and relate that to roadway safety. And then after that, we're going to talk a little bit about the interpretation of the models. So I'm going to create a model which I am calling NB3. And I'm simply going to copy and paste this line of code from up above. And perhaps you can't tell from the video, however, I started and stopped recording. But since this is the first time today that I've been in this document, I'm going to want to make sure I read in my data again, call my package. I'm going to put a pound sign before this code. This essentially is telling, if I were to knit this file, I am telling the program not to run this specific line of code. And I'll do the same here as well. And I'll bring in my recoded AADT variable. Okay. So we have curve radius in our data set, but we have to determine how we want to incorporate it. Do we want to transform it or what we want to do? And I think the first thing we're going to try and do is going to be a log transformation. Now I could consult with my data set. Okay, I'm looking for a variable that is going to describe the radius of the curve. And I can see I have already coded ln rad feet, but I want to work with this just so I prefer to do these kind of conversions in here. So we can see based on this period that this label in my data set is actually either a hyphen or a space. So we discussed that a little bit before, but I just wanted to point it out again. Okay, so our model is going to consider that demo AADT, which is the directional AADT log transformed. We're also going to use an offset variable, which is the log of the curve length in feet. And then we're also going to look at the log transform of radius in feet. So now I will run this model. We can see that it ran with no problems. And now let's look at the summary. So for this simplistic model, we can view our coefficients. And we can see that in general, we have a negative intercept, which is fine. We kind of expect it. It's fairly common in statistical modeling. We have to remember when we exponentiate this value, it would be positive. So we're always predicting a positive number of crashes for any given AADT. Here we can see the effect of AADT, or traffic volume, on our model, and we see that this coefficient is positive. So that indicates to us that as we increase the value of AADT, we would in fact increase the number of crashes we expect. And this is consistent with the existing literature and just what we believe to be true. There's more traffic, there's more opportunity for crashes. We also have our log of the radius in feet. So we can see that we expect that as we increase the radius of a curve, we would see fewer crashes, and that's what's being captured by this negative coefficient. So intuitively, our results make sense. Again, we can monitor our various goodness of fit metrics. So we'll just concern ourselves with models 2 and 3. So model 2, we can see, had an AIC of 16.33.9, whereas model 3 had an AIC of 1606.2. So based on AIC, we would conclude that this model that includes the curve information the curve radius is a better fitting model. One thing we may also be interested in is running an intercept only model. If we're interested in comparing AIC across models, it might be beneficial to have the AIC for that intercept only model. So I will do that here. As you can imagine, we'll call this NB4 just to keep with our convention. To specify an intercept only model in R, rather than include the names of any of our variables, we just use the number 1. So here we can see initially that our AIC is 718.4. So what that's telling us is that our previous models were both improvements over that intercept only model, which is good. We can also see that the decreasing trend, so that so far we have our model has continued to improve. So one thing you may or may not have noticed about R is that it's really easy to go back or to track the models that you've developed by naming them differently, and it's easy to go back and rerun an old model or pull that. So for instance, all I have to do if I want to look at the summary of my model NB2 is just run the summary code. There's no need to actually run the model again, and it will output it. So that's very useful when I'm trying to go back and remember the various model iterations that I've done. So in closing, I hope you found this tutorial useful. It's by no means a comprehensive tutorial in the negative binomial model or the applications of statistical modeling in traffic safety. However, hopefully this will have given you a skill set that is good enough to help you move forward in the various analyses that you might want to conduct. So thank you and good luck.